Mr. Khanolkar and his Metalcraft Industries is a well-known name in foundry toolings. He has an experience of more than a decade each in Tata Motors and Kirloskar Ferris Industries Limited. His visits to patent shops in Europe, United States, and Japan have enriched his knowledge, and he has worked on toolings for almost all the tractor manufacturers in India. We will definitely benefit from his 35 years of experience gained while working in industry designing and manufacturing toolings, where the percentage of first time right is very high. I request Mr. Khanolkar to start his presentation. Thank you.
Before I start with my presentation, let me share my experience on the day when I came to Tata Motors to join the company. Till the time I was waiting for doctor to arrive, I was wondering that I have done my engineering 4 years in an engineering college, now going to join a big Indian automotive industry. But there are some unfortunate people in this company who are spending their almost their entire life on those cast iron blocks. And I don't know why, whatever hours, couple of hours I was staying there, I could say nothing moving. They were using hand grinders and hand tools and trying to give some shapes to those blocks. And in a way, I was pitying them. I was thinking that how one can spend almost his career in such with such blocks. Doctor came, the medical happened, and we got appointment later, joined Tata Motors. We had a long and big training program of 2 years. I completed that. And in the last leg of my training, I was asked to join production engineering division. We went to see Mr. Yogendra Nath, who was heading that division those days. And he directed me to go and join patent shop. I searched for patent shop, came to the shop. Those were the days 40 years ago. Technology was not evolved to the extent that it is today. But still they were producing castings. Same castings are being produced in India even today. And then as I entered into that area of pattern making, I realized, although in those days nothing was seen moving or developing in a fast manner, pattern maker is the only person who can convert, or who has been given job of converting two-dimensional inputs into a three-dimensional object. That is the only profession in mechanical engineering where you are given inputs in the form of a 2D drawing. That was, of course, 40 years ago. Today, you get a CD or a CAD file on email, and you convert that two-dimensional thing into a three-dimensional world. So that is the entry of any automotive. So that is the contribution of a pattern maker or a pattern designer in engineering industry. And when I realized this, I started taking more and more interest in all the activities related to pattern making. And then I realized this is perhaps the most interesting department, division, section of engineering of any automotive company. So universal deliverables have still remained the same: quality, time, and cost. But today they are required simultaneously. At the same time, you should provide the best quality in the fastest possible time and lowest possible cost. Now, with these challenges in mind, let us think how they apply to the task that we have to perform, that is to design or manufacture or to develop a foundry tooling. Specific demands in today's context are less casting weight. Everybody wants casting weight to be minimum, and of course, at no point the casting wall should be less than what is expected. Machining allowances. A lot of machining cost is a function of the machining allowance that we provide. So lesser the machining allowance, lesser the machining cost. Surface finish has to be good. Prompt response to modification. the tooling should be designed such that it is possible to modify those tools whenever the modifications are expected, desired, or any changes are to be made in the tooling. Rejection, of course, minimum possible. This is again a debatable point because whenever something goes wrong in a foundry, people gather around the pattern or the core box and decide to do something on that. Same pattern or the same core box was giving a considerable good amount of casting, and suddenly the rejection shoots up, and people start talking about what is to be changed or what is to be modified in the tooling. So I'm saying less rejection, but wherever tooling it can be positively attributed or the reason for rejection can be directed towards the tooling. Of course, tooling should be a lowest cost and simultaneously the competition has to be taken into account. With these specific demands of today, let us move further. Now, at this point of time, when first point that I've said is less casting weight. Now, casting weight, everybody wants minimum casting weight. I got last week only, I got a telephone call from a very senior person in a foundry he asked me, what should be the tolerance on the casting weight? The drawing says 70 kg. My casting is says 71 kg or 72 kg. Should my customer pay for it? Point here is, my explanation to him was, weight is a function of volume into density. Density is defined by your composition. Volume is defined by your drawing. Every drawing will have some acceptance limits, generally governed by an Indian international standard IS 8062. The castings that we use for mass production or for automotive applications classify or required in the category CT8 to CT10. CT10 is the coarsest of the range and CT8 is the most accurate. Now this range will say casting of the size of a cylinder block will have say plus minus 1 or 1.5 millimeters of dimensional tolerance on the thickness. That means plus minus 10 to 15% is the tolerance on the thickness of the casting. Now, if you consider volume into density is weight, density is fixed, the volume is going to vary because the applicable tolerance is plus minus 10%. That means there is nothing like a specific weight or the fixed weight for the casting. The casting weight is going to vary by the amount of tolerance that is allowed on the dimensions. If you take this into account, generally, the target is to keep the required wall or aimed wall at middle of the tolerance. That anybody would say that if the range is 5 to 7, let me manufacture my tooling at wall say 6. So that whatever happens, the inaccuracies come, my casting remains in the range, center of the range. And of course, my weight will also remain in the center of the range. But there is something called tool wear. The pattern what is of X dimension today, after producing 50,000 castings will not remain the same. In olden days, even German tool makers used to give wear allowance on the patterns, 200 microns or so. That will also translate into some amount of extra weight. Then there are movements of the cores, and all taken together, the casting is going to vary. It is not like pressure die casting. It is a sand molding process, and the casting weights will vary. Of course, within limits prescribed by IS 8062, the closest or the most accurate range would be say CT8, so CT or high pressure molding line. Whatever is the tolerance applies on that will also apply on the casting weight. The dimensional tolerance will translate eventually into weight tolerance. This has to be understood not only by the foundryman, but this has to be made understood to the purchaser or the buyer of the customer. Machining allowances, again, the minimum possible machining allowance is a dream of every machining person. But the casting machining process takes reference of some pads or positions on the casting, and dimensional variations from that pad to the machining surface will also play an important role when we talk about machining allowances. Good surface finish, generally it is said or people expect that if the pattern is very fine, smooth finish, the casting finish will be good. But this is half truth or no truth, because largely the casting surface finish depends on the sand that is used. Second, particularly in Indian context, why surface finish of the casting appears to be bad because of various modifications done on the patterns, various levels of MCL applied on the patterns. So this unevenness creates an impression of bad surface finish. If you have a pattern with a poor surface finish, of course with good draft angles, and the mold can be made, the pattern, if it is smooth, no additions later on, the casting surface will definitely look good. We'll move to the next slide. So having understood this concept, we had to start with making of foundry tooling. The first step that I consider here is the scope finalization. Many times, if some pattern makers are attending this session, generally you are given or we are given the component drawing and asked to quote for the tooling cost. But what about scope? Which molding line, what type of cores are there, on which machine the cores will be made, whether the foundry production facilities have enough capacity to produce the required number of cores. Always there will be some bottlenecks in the foundry. So if you design or develop a core box in one of the bottleneck machines in the foundry, the entire production will be restricted by that one small bottleneck machine. So scope finalization is a very important thing, which in my opinion should involve each and every person who is going to be associated with production of that casting, from purchase department, from marketing, from methoding, from core shop, from molding line. So all should sit together and finalize the scope, and based on which toolmaker can work out his quotation and work out his schedule of delivery. After the scope is finalized, as I said, take with full and active participation of all the concerned departments, design of mold scheme. Design of mold scheme is something where we define how a casting will be produced in a foundry, how various elements of casting making will be coordinated. Here I expect that past experience is taken into account, not that past experience is to be copied, but let there be no reinventing of wheel every time. Then today's context, 3D modeling of cores and patterns, it is much easier today. But that at this point, let me mention one thing which creates huge amount of problems at a later date. Generally, today 3D models of the customer's casting are given to the toolmaker. Now there are 4 types of wall thicknesses on any given casting. One is drawing wall, the wall that is mentioned in the drawing. Of course, that will be with some tolerance. based on CT8, CT9, CT10, IS 8062. Now this wall thickness, many times even customers don't give tolerance on the drawings. So that has to be demanded and finalized and accepted or rejected before we start with the tool making. So one is drawing wall. Then comes the model wall. Now in today's context, with so many analytical softwares being available, the same casting models or the same part models are subjected to various analytical softwares. So it is always desired to design the casting which is given for failure analysis at the lower side of the wall thickness. So if the range is 5 to 7, any designer who wants to test his design for failures will design it at 5. So you are given generally the same model that is designed at say 5 millimeters. And the tolerance is given to make things easier for product designer 5 plus 2 minus 0. So at the starting, you have a casting model which is 2 millimeter lower than the maximum that is acceptable, or maybe 1 millimeter less than what your casting should be. Effectively, if you calculate the weight of that casting, is expected to be 10 to 15% less than what you eventually supply as the correct casting. Casting weight. So this is the second, that is the model wall thickness. My general observation is it is at the lower side of the tolerance. Now third is tooling wall thickness. What should be the wall thickness on the tool? Given the wall thickness on the casting model, wall thickness on the drawing with tolerance, what should be the wall thickness that is aimed or expected on the tool? I would not go into the entire discussions and debates, whatever has generally happened on this, but my advice would be from lower end of the tolerance, cover 75% of the tolerance. So 5.5 to 7, if it is the range, aim your tooling at 6.5. So 75% of the tolerance we use for various boundaries, various accuracies, inaccuracies, and variables. With all these are the three types of wall thicknesses we discussed, and the fourth is the one which actually happens on the casting. Now there are so many other issues like mold swelling, core lifting, core floating, core distortion, and so on. All said and done, in conclusion, we can definitely fairly good to say, correct to say, we can aim at 75% above the lower tolerance. This is 3D modeling of cores and patterns. While modeling the cores and patterns, we have to do all this, take into account the variations, add the extra material wherever it is required. Of course, have a big debate with the customer and the buyers about the tolerances on the castings. And with this 3D model of the casting is prepared once again or remade by the tool maker or the pattern maker or the foundry designer, which we can definitely say this is the casting model. So from product model is the transition to the casting model, where we have also added the machining allowances and then had a discussion about where all the which are the places where customer would like to machine, and of course to take care of the correct dimensional tolerances. Once this casting model is made, this can give you a fairly representative casting weight, and if that weight can be, this weight can definitely be considered as the weight that eventually your casting will have. It is always advisable to give this casting model to the end customer for approval. Once they approve it, there'll be less fights and discussions and debates later on after the casting is made. Then once the casting model is approved, we can work parallelly or simultaneously to do 3D modeling of cores, patterns, based on various guidelines, which will come a little late, or maybe in our second lecture, we'll cover in more details that part. Then design of actual core boxes, fixtures, pattern layout, approval discussion with user departments in Foundry. Because when I take pride in saying that I'm associated with this field of Foundry tooling for 40 years. But today, in mechanical engineering industry itself, it's very difficult to find people who have spent more than 10-20 years. Because after 5-10 years, people think of moving to either a non-engineering job, or I would say हाथ जिसमें नहीं काला करना पड़ता है, that kind of job, or simply to IT kind of fields. So in every department, you will have people who either don't have experience or have experience of a very short duration. Because of this, every tool, every drawing, every model needs an approval, at least some discussion with user department in Foundry. This helps if you do it at soft stage, 2D design stage or 3D modeling stage. It definitely reduces actual rework on the tool when the tool is made ready. The next stage is raw material procurement. Everybody knows EPC or thermocouple patterns are made to procure the castings. Parallelly, you buy the standard parts, then pre-machining of raw casting, CNC machining, assembly, and inspection. Now we'll spend some more time here on scope finalization. That was the first point in Moleskine design. This is a very important activity, but it is generally not given its due importance in the beginning. Because whenever a new order comes to a foundry, everybody is excited and to deliver castings in a very fast and such a manner that customer is very happy and all that. And in that, people overlook or shortcut such things like proper discussions with user departments, proper analysis of our own abilities, proper understanding of what customer needs. This all takes a backstage, and something gets manufactured. Some toolmaker is hired who also doesn't take that much efforts, which I'm discussing right now. And some tool is made, casting is made, and then almost 3 to 4 times time is spent in modifying and coming to the coming to meet the requirements of the customer. Foundry purchase, sometimes end customers purchaser, in this case, maybe an automotive company buyer, development department in Foundry. In many cases, entire cross-functional team in Foundry are involved in this activity. In fact, they should be involved in this activity, not at the same time, but at different times. Now, here there is a catch. If all these people get involved into scope finalization at various stages or various times, as and when they can, it becomes something like maybe there are too many cooks. Many times the recipe is spoiled. This leads to changes in the list of toolings needed. The core shop will say that I don't have capacity on this machine. This machine cannot produce water jacket. There are some dimensional issues. There is no accuracy in my machine. There is some hydraulic pump is gone and whatnot. And I would have preferred this core box on this machine. Now this comes when almost toolmaker is almost procured or he is halfway through manufacturing of that core box, and then the requirement comes that the machine needs to be changed. So which leads to delays and cost escalations. Pressure of deadlines affects the quality also. Why I'm stressing this point is because if scope finalization is given its due importance right in the beginning, we we save at least 20 to 30% of efforts, which we are forced to take later on. So now we start with the tool designing, that is the mold scheme. The first thing is list of tooling. Before we make the list of tooling, now here I would like to mention something like family doctor concept. When we were small, nobody used to go to a specialist directly. There used to be a person, maybe a MBBS doctor or a local doctor, a locally learned doctor. But he would look at the patient, he would know the everything in and out of the patient, his habits, everything, his family background. Without asking for so many tests, he could give the medicine. Now that kind of thing is missing today because everyone thinks that he is a specialist or there are so many specialists. So list of tooling, correct definition of tool tool material are the two basic things which need to be understood and taken into account in a manner where we have asked everybody, we have consulted everybody, and the list is not going to change hereafter. Correct definition of tool material is also important because many times companies want 50 castings, 100 castings for their initial trials, and they expect that without spending second time for the same tooling, they say that if everything is acceptable now, we would like to start mass production from the same tooling. Now, at this point, the correct definition of tool material becomes important because although since they want 50 or 100 castings, but from the same molding setup, we definitely cannot produce that kind of castings or automotive grade cylinder blocks and heads using wooden patterns. We need metallic patterns. But in metal also, or the metallic patterns also, there are various tool materials like P20 pre-hardened, H13 hardened, SG iron, grey cast iron, aluminum. Aluminum, wood are ruled out in today's context because today's CNC machines make no difference as far as the time required is concerned for machining on aluminum or whether they are machining on cast iron. Of course, H13 and P20 will take slightly more time, but not many times more time. So correct definition of tool material is important. If you want to have first some initial parts, then they will be made subjected to testing assembly at the customer's end, and then maybe possibly a pilot lot or a bigger lot. Then it's always better to go for cast iron tooling or SG tooling instead of going for P20 or H13 tooling. But if we don't take this into account, people are very adventurous and start with H13 tooling or P20 tooling, pre-hardened steel tooling. And if the modifications come on the same, because the product is also in development stage, the cost of modification and everything cost of modification is very high. Then we have to think about number of cavities. Now, anybody would expect his molding line or his core shooter should produce maximum possible number of cavities. But how the gating will be done, does it need any risering, etc., external feeding? Taking all that into account, the number of cavities has to be decided. Now, why I'm stressing this point is because when any toolmaker quotes for a foundry tooling, he expects 1 or 2 cavity patterns, and whether it is 10 cavity or 2 cavity or 4 cavity will largely vary the tooling cost. Then core combination in core boxes. In casting such as cylinder blocks and heads, there are shell cores required, there are cold cores required, there are chunky cold cores, there are thin cold cores, there are chunky shell cores, there are thin shell cores. So there are various types of combination needed in a particular casting for making that casting, and combination of that is very important. Now, when you start with making of mold scheme, you just read through the notes on the drawing, and there will be certain dimensions which need special casting tolerances and special gauging needed to achieve them. Unless if this is overlooked and we make the entire tooling design, entire methoding into consider case of Maruti 800 cylinder block. This is 3-cylinder block, but all 3 cylinders are made from one single crankcase core. So variations from first bearing wall, second bearing wall, third bearing wall, and last bearing wall are minimum because they all come from one unit. Whereas if you have 3 different cores, each core will have some variation in thickness, each core will have some variation in core making, and so on. And definitely that will reflect on your web wall thickness. So whether machining is required, what kind of draft is allowed, all these factors will be important if the product design needs certain machining or no machining in those specific areas. So review of special casting tolerances and special gauging needed to achieve them. This small effort in the beginning to decide exact scope of tooling will lead to macro benefits in overall tool life cycle, but it must involve all concerned, including production department in the beginning only. If somebody comes at a later date, maybe a month or two after, when toolmaker has proceeded with his half of his tool designs, maybe material is procured and somebody comes and asks for some changes. One, a lot of energy, money, resources are wasted, and second, the time which can never be regained. Once the scope is finalized, rest of the tool design can proceed without much surprises and delays. This is something which toolmaker can do at his own end, but the earlier part which I discussed needs collaboration from all concerned parts and departments in Foundry. Mold scheme again is a document which outlines how a casting is processed in a foundry. It also acts as a starting point in tooling development cycle. It is a bridge between foundry and a pattern maker. With whatever experience that I have, my advice to the foundries would be make a methoding drawing at your end, involve all your departments, all your persons, all your expertise, and make a method drawing. And give this method drawing with a proper tooling list to your pattern maker so that he will not be disturbed. There'll be no changes, no surprises once he starts his work. So it has to be a starting point, and it is a bridge between what foundry wants and what a pattern maker can deliver. Objective of mold scheme in simple words is to produce a good casting in most economic way. Whether core should be made hollow, or whether it should be made on vertical core shooter, horizontal core shooter, all this thinking has to go into this document. Mold scheme designer requires thorough knowledge of practices followed in foundry, for which the tooling is to be manufactured. So there is nothing like universal mold scheme. It also means that a good mold scheme for foundry A may not work out to be as good for foundry B. Here, in my experience, I've seen many times the foundries are offered tooling made for some other foundry because that foundry is not doing well, rejections are more, they have some labor troubles, And then customers think that shifting that tooling from foundry A to foundry B, and if such toolings are accepted, my experience is 20% of the tooling can be utilized and 80% paraphernalia has to be regenerated to suit the foundry's requirement. Again, it comes with so many limitations because it is made with somebody else's expertise, somebody else's experience, somebody else's practices, not necessarily sufficient or adaptable for the new foundry. If at mold scheme design stage, all areas related to casting making are properly addressed, it saves a lot of trial and error type of rework at later stage. A mold scheme is also a form of tooling. All basic principles applicable to any good tooling apply to mold scheme in addition to foundry specific considerations. Most of the activities in engineering industries, such as machining or assembly, involve much less variables as compared to variables involved in a foundry. Just to list, if I'm doing machining of a part on my horizontal machining center, I have 5 or 6 or 7 variables at the most. Whether coolant is not there, what kind of feed I'm going to use, what kind of speed I'm going to apply. These variables involved, maybe I can say that the type of the tool is also a variable, but they don't count beyond 10. But if you talk about foundry, the number of variables exceeds maybe 250. The sand has got enough number of variables. The core box has got, core shooters has got so many variables. Metal itself is a variable. Everywhere there's so many variables. So the foundry designer, the method designer has to be more experienced and expert, or at least have understanding of all these variables which can affect the quality of the casting. After that, let us move on to consideration that should go into design of a mold scheme, which can be classified into following groups. 1A is the product related considerations. Comparison with sample casting. In many of the situations, particularly in Indian context, we have seen the casting that is actually going on the vehicle or going on the product is different from what is shown on the drawing or on the 3D model. Definitely there is a gap, there is a lapse in updation. But if you follow the component drawing given or the 3D model given, which is different from the actual sample casting that is being used, there are surprises expected at a later date. How to avoid it? A very simple way is the moment you start notice from your customer, ask for the sample casting. Or sample casting has to be there when you start. Generally, half the design of the tooling is done and the sample casting arrives. Now, this sample casting has got so many indications which will help in deciding how to make a good casting. It will show you which part is in cope up, which part is drag up, what are the wall thicknesses actually aimed on the casting and what is there on the drawing. Are there any additional bosses, pads, references on the casting? What are the identification system that is there, which is generally not shown on the drawing? So all this can be taken care of if sample casting is made available and compared with when we actually start with the tooling. Machining allowances. There has to be a conclusion. The foundryman would say, give maximum possible machining allowance because I don't get casting rejection because of lack of machining allowance. The machine shop fellow is going to say that I want minimum machining. So there has to be an agreement before. Casting tolerance is expected, casting weight I discussed earlier on this subject. Initial reference points for machining. This is a very sensitive issue because before we understand, there are certain customers who are very good in defining initial reference points on their drawings. They generally use 3-to-1 location. Then what are the locate points? What are the rest points? What are the clamp points? Everything is properly mentioned on the drawing. With 3D models, it is little difficult to correlate it with 2D drawing because people don't look at 2D drawings when they have 3D models. But it's very important to identify these areas. So if this is an initial reference point, then there has to be less draft, no extra material, because the entire machining process is set using this. Then extra material on the casting wherever intentional, unintentional, or the process requirement. And the last and more important is casting identification. Everybody wants casting identification, this ISO and so many things. But 50% of the drawings I have seen don't show casting identification in at which place it is required and in which fashion it is required is not mentioned. So this needs to have clarification from all the related participants. So these are the specific considerations related to the casting. Then there are general considerations. They are like the foundry elements which are added to the cores, the patterns like fin, the sand cord, the crush groove to avoid metal leakage outside, the contraction allowance. Contraction allowance is, of course, volumetric contraction of the metal from the point it is solidified till the point it comes to the room temperature. But at the same time, the cores inside offer resistance to this contraction. So the contraction allowance will vary on the hardness or softness of the mold outside and the rigidity of the cores inside. So all cored casting from inside outside will have a different contraction allowance from non-cored castings. Shell cored castings will have a different contraction allowance. This is a very important consideration because the machining allowances are directly related to this. If the contraction allowance is very correctly established in foundry, then they can think of controlling machining allowances. But if we are not sure about what contraction my casting is going to make, or a smaller casting is going to have a different contraction as compared to the bigger ones, percentage terms I'm talking about, then machining allowance also needs to vary to that extent of the uncertainty that you have on contraction allowance. Then what should be the sizes of the core prints? Core prints will have to support the casting into the mold. So generally people think my core is weighing 500 kg. The sand, supporting sand or the resting print of the in the mold should be able to withstand those 500 kilograms. Assuming that 2 kg per centimeter square is the strength of the sand, which I should safely consider. For a 500 kg core, I need 250 centimeter square of the print. But this is half truth or no truth. Because the moment metal comes in, the buoyancy force starts acting on the core. And considering the difference between the density of core and density of metal, the upward thrust of the buoyancy force is almost 5 times of the core weight. So if the core is being 500 kg, 2500 kg upward thrust comes when the core is submerged on the metal. That is if the core is solid. If hollow, it will be more. So this consideration has to go into deciding the sizes of the core prints. Then print clearances. Anybody would expect that print clearances should be minimum possible. So that there will be lesser variations on the casting, variations in the core placement, and effectively lesser variation on the casting dimensions. But print clearances are required again to take care of variations coming because of process. Your core painting is not uniform. If paint is coming on the areas where it is not supposed to come, across the parting, if there is growth in the cores, all this will lead to or demand clearances on the prints to be increased. So, print clearances is the function of the discipline that can be further maintained into various departments of foundry. The core making is perfect. Every core is checked. Every core is certified that yes, it is at the design thickness or design dimension. Then maybe print clearances can be slightly tighter. Draft angles, of course, foundry will be happy with maximum possible draft angle. The customer doesn't need draft angles. The draft angles are given because of the demand from the foundry. So draft angles is again a compromise between user, that is end user, and the foundry. Core resting in mold, same as the core prints I talked about. Chaplets, cope drag selection, which should go into cope, which should go into drag. The old casting generally give the reference castings gives a good idea about this. And again, what kind of earlier toolings, the practice that has been followed. Then productivity related considerations. How many castings per mold we would like to make? This is more important when people make small castings. 42 castings per box or 30 castings per box. And because one size of the riser is changed, from 3 rows it goes to 2 rows, so 10 castings gone. So it's very important consideration to decide number of castings per mold. Maximum number of cores per mold. Now my molding line is running at say 60 molds per hour. I can fit say 10 cavities of patterns in one mold box. And each casting needs 5 cores. 10 into 5, 50 cores I need to place in that speed of molding line, which is 1 per minute. So this also has to be taken into account, how many cores I can place into the mold to match, to not to stop my molding line for want of cores. More than one type of castings. Generally, people say that itna jagah baki hai, can you accommodate some more casting, some other casting on this? But this is only an idea. I never practiced, or I don't think anybody's practiced this. Productivity of the core boxes. Too many cores in one core box reduces the productivity. So lesser number of cores accommodated in core box, maybe with higher productivity, could be a good answer. And other production aid. Then core related considerations, parting lines of cores, core resting, core location, core handling, core hollowing, core to core fouling, blue tip reliefs, special considerations for blocks and heads. These are the considerations. Why I'm saying mold scheme is a very important document, because when we talk about core prints, we don't think of all these things. But unless a proper thought is given to all these points, whether core needs to be made hollow or not to be made hollow. This is a big debate used to happen 20, 30 years, 40 years ago, and even today. Now people make, because for the sake of it, people make cores hollow, particularly crankcase cores in a cylinder block. Then after some time, they find metal going inside. So metal is costlier than sand, so they decide, okay, we'll make it solid. So another person gives an idea that let us make a plug core, make the core hollow and plug it from backside. That's an additional operation. So whether one should go at all for this or he should not, Again, making a core hollow or making a core solid will have some implication of the eventual contraction also. So all that this has to be given a thought at the Moleskine stage. Core to core fouling, in one or two cases or few cases I have experienced that we have made the core, we have made everything, we have made core setting fixture, but the sequence is not taken into consideration. So one core cannot be placed after the core, second core is placed, and second core cannot be placed after first core is placed. So maybe the core has to be split. Put half the core before, then put the second core and the third core to cover it. So all this has to be given a proper thought when we design the Moleskine. Glow tip reliefs. Cutting glow tips and trimming them is a manual operation, generally takes time, not done properly, can reflect on the quality of the casting. So it is better that pattern takes care of that excess tip that remains. Special consideration for blocks and heads. Because of particularly because there are multiple number of posts and cumulative errors can get distributed, and then these cumulative errors can lead to dimensions firing out of tolerance. Mode related considerations, draft angles, particularly in self core pockets. I am yet to see a foundry where half degree self core can confidently be made. So accept this and let us say that any self core that we are going to make will have 3-degree draft angle. Discuss with customer, get it modified, and start with the pattern making. Location of screw is again more related consideration because do everything and then realize that screw cutting machine doesn't reach that point. So all this today in today's context, since CAD/CAM is there, all this can be standardized. And when you make a pattern layout, the screw will always be visible and you will easily understand that yes, I cannot place casting like this or make this kind of layout because the screw cannot be taken to this place. Parting line leakage, what is the minimum sand wall? Then fettling related considerations. Fettling related considerations, generally, whenever we used to ask for sample castings, we used to ask for unfettled sample casting. So that gives you a fantastic information about how the casting is made in earlier foundry on the sample foundry. So parting line selection, horizontal vertical fin, the fin parallel to the wall of the casting or perpendicular to the wall of the casting. It depends on the process for fettling that you're going to employ. Fettling templates and gauges, gating and venting system, good drafting practices, initial reference points on the casting. So these are the fettling related considerations. For example, just to explain, if there is an initial reference point defined on the casting drawing, it is not defined on casting model. So if you don't see the casting drawing and you that pad goes into cope and somebody puts vent pin to take care of blowhole or gas problem, you have damaged the casting reference point. So every time it is overground or underground, the entire casting machining is going to vary by that to that extent. After having talked so much on this, there are some people who are not exactly aware of foundry tooling or their benefit. This is typical representation of a cylinder head methoding. This is the magenta color is base core, then these are the port cores, then the water jackets. Today with 4-wall cylinder heads, it has become almost impossible to make a single water jacket. So you have to make a split water jacket. Place bottom water jacket first, then place the port cores and then top water jacket, test it, paint it and so on. This is typically how it will be gated. This is filter seat. This is typical package for a cylinder block. This is a typical high pressure molding line pattern. This is a twin type pattern where two blocks are joined back to back. Now come to the. We started with understanding the customer's requirement, involving all the departments in Foundry. Then developed, defined, perfected a document called mold scheme, where entire whatever thought, all experiences have been pulled together and a document has happened and approved. Then it's easier to extract cores from that and then decide on which process the course will be made, whether it is shell or whether it's cold. Again, shell will have two options, vertically parted, horizontally parted. Cold also will have two options, vertically parted, horizontally. So once we decide that this core has to be made or made by shell process and on a vertically parted core shooter, the first thing that has to be decided is core parting. Then comes the door hop or ram hop or fixed hop or moving up selection. Because most of the machines will have ejection or core extraction system on one side of the machine. If it is a door opening type of machine, then door is supposed to carry the core. So deeper portion has to come in door. Again, there are other variations like what temperature to be kept and ram ejection, the ejection from pushing of the core from the opposite side to the door hub. Then what should be the blow tip locations? What are the ejector pin locations? Heater holes. Because today electricity also getting costlier day by day. First heating the heater plate and then the core box is not a really economical way of heating the core box. So people prefer heating of the core closest to the core surface, that is in the core box insert itself. Types of heaters, which type of heater that Foundry standardizes upon. Pneumatic cylinders, standard as far as possible, hydraulic, pneumatic, whatever. Then core box loading and unloading, this is a very important consideration generally given a backseat. Made a huge core box weighing 3 tons and don't know how to load it onto the machine. Critical fouling point on the machine. Many times we tend to use the machine to the extreme end of their capacity. While loading or the opening of the core box, the core box insert fouls with the door of the machine. So this all needs to be mathematically or graphically checked before we actually start manufacturing the core box. With 3D modeling and 3D softwares, it's much easier nowadays. Then blow plates are involved, ejector plates are involved, and core identification, because which traceability and identification. So core identification, knockout pins, clamping slots, use of standard drawings and parts, typical core making cycle. So whosoever designs the core box has to go and see at least for half a day on the machine and see how the core box operates, how the machine operates. Write down a tool typical core cycle and then start the core box design. A lot of rework can be saved if the designer understands what he is going to design. Placement of clips, steels, etc. Many times the methoding needs some metallic parts inside the core. So whether that can be placed into the core, whether under flow or pressure of air, it doesn't get disturbed, damaged, dislocated. So thought has to be given to that. Weight of the core was, many machines have got some weight limitations. And on other side, we want a big core produced using the same machine. So core box weight is again a very important consideration. Pad clamp, that is joining of the two halves and safely loading it onto the machine. This is a very simple core box required and used for a core shooter where heater plate is heated. You can see also additional holes, but the ejector plate that used is that of the machine. This is, I would say, simplest shell core box. Then this is slightly advanced version where heaters are there. The ejection system is there. The ejection plate has to be guided. Then there has to be a bolster. Then come to horizontally parted shell core shooter. Top bottom selection, selection of blow locations. Now, generally a debate is made whether horizontally parted core shooters are good or vertically parted. I would say each has got its own advantages and disadvantages. But cores which are very difficult to make can be made relatively easily on a horizontally parted shell core shooters. Because the area that is available for providing blow tips is much more as compared to vertically parted core shooters. Second point is the sand has to travel lesser distance on a horizontal core shooter. And sand also, in case of cold, it is gas also. So cycle times are generally faster on horizontally parted machine than on vertically. So top bottom selection depends on the extraction mechanism that is available on the machine, selection of blow locations, selection of bottom ejector pins, core unloader positioning, the extraction mechanism, guiding mechanism for blow plate and ejector plate, floating arrangement in bottom. Because heat is involved, it's a shell. So if the top expands and bottom doesn't expand to the same extent because of the temperature difference, and the bolster on which the core box inserts are mounted are at a much lower temperature. So if no provision is made to allow this expansion, the warpage is going to set in. The moment the core box is warped, the core dimensions are going to get fired. Transfer core shooters nowadays are not in use, but it needs a burner plate, blow plate, or separate kind of design. Hand operated loose pieces, whether they are allowed, whether they can be used in a foundry, again needs discussion approval. This is horizontally parted shell core box. You can see it is much complex as compared to the vertically parted. Cold box again, it is almost similar. The considerations are same. Maximizing output is the consideration. Core box core combinations. Core box combination is also important because suppose a foundry has got 20 core shooters, then they would have no problem in allotting 4 or 5 core shooters to make a one particular casting. But if they have say 5 core shooters, they cannot use all 5 for producing one particular casting. So core box combination, which course can be made in one particular core box, will depend on the availability of core shooters, positioning of the cavities, bigger cavities in the center or the delicate cavities in the center or whatever. Blow tip size and positioning. Details we'll discuss some other time because already we have spent more than an hour. Blow plate, gassing plate. I'm just listing the elements involved. Same as shell, the difference is we are dealing with amine gas here. So leakage of amine gas has to be prevented. So the whole circuit is supposed to be gas proof or leak proof. This is a typical vertically parted core box. Bolster, core box insert, ejector plate, guiding arrangement. Horizontally parted core shooters, similar. But same as shell horizontally parted. Only difference is heaters are not there. and gas passage and gas leakage to be avoided, and gas passage systems are to be provided. You can see these bolsters closed with a cover plate, which otherwise was open in shell core box. Today, with higher and higher numbers required from any foundry, the modern core shooters are employed by most of Indian foundries. They need very, very elaborate foundry toolings, cost of which can be almost 3 to 4 times than conventional tooling. But their productivity outputs also much higher, dimensional accuracies are much better. This is a typical vertically parted Corvus, which weighs around 8 tons. This around weighs 6 tons. So this kind of tooling, again, pre-hardened P20, even the bolsters weigh with 1200 kg each are in AGN. So you can imagine the cost involved. And more than cost, if a design goes wrong, or the selection, or there is a major modification at a later date, you can imagine the cost involved in this. This is horizontally parted again, cold box core shooter, different angles. Use of templates I talked initially. Whenever we make a core, we have multiple cores, particularly in cylinder blocks. And when all these cores go onto core seating fixture, and each core, say, is produced oversized by 0.4 millimeters or 0.3 millimeters, which is normally expected, 8 cores will mean the cumulative error is 2.4 millimeters. Now, this 2.4 millimeters here will definitely reflect on some casting dimension from one end to other end getting fired by 2.4 millimeters. How to avoid this? The thinking has to go into it. Now come to the final core setting fixture. Design a bottom half 3 to 1 location of cores. So each core has to be properly located. Gravity is going to settle the core into place, provided 3 proper resting, 2 restings against to define second axis and 1 for third axis, or any other kind of location, but the core has to be arrested by at least 5 degrees of at all degrees of freedom. Locator positions. Locators should not come in casting area and all that. Position of cavities and pattern layout has got a direct relationship with picture layouts. Core placing sequence, whether trolleys are required, use of core trolleys, pneumatic cylinders, foolproofing, orientation of the casting, maximum number of cores in FCSF. I spoke about this a little while ago. If there are 20 cores, you manually somebody has to keep those 20 cores into the picture bottom half. If it takes longer time than what the line can provide, maybe core packaging, making of a core package before, or having 2 bottom assembly fixtures can be thought of. Clearances, tie rod, use of shims. Design of top half, the half, bottom half we have talked about. So top half which sits on, on the bottom half and takes the core, clamps the core, picks up the core and lowers into the mold. This is a typical bottom half of the picture. This is bottom half of the picture without core. Top of the picture placed onto the bottom half. Then we are coming to the end. Let us talk about casting averaging fixtures. Now, this is the first question would be why casting averaging is required. In Indian context, we have 60-year-old, 100-year-old, 60, 70-year-old designs running for manufacturing today. And we have modern castings also being machined. Now, the way the foundries have evolved, the machining processes also have evolved. Earlier, I have seen in one of northern Indian tractor manufacturers, where each casting when taken on the machine, it is marked with a reference line. That reference line is again taken into the machine setup, and then locate that machining line and start machining. So each casting was viewed separately. Then came the concept of averaging fixtures, because foundry has made the casting and said that my casting is okay. It goes to machine shop and something there is after machining there is some fouling reported or no machining reported or excess machining reported. To avoid all this, the product designer has said that I'll give 3 spot facings and 2 dowels, and let the foundry generate these 3 references, the rest points and reference dowels, and I'll machine based on that. These locations remain till the end of the life of the casting. So if the casting is wrong with reference to the reference points, the foundry is responsible. So that's how came the casting averaging concept. So foundry will average out the casting, ensure that proper machining allowances are there, there is no movement of cores, whatever the fouling parameters are needed, they are checked, and then 3 spot facings and 2 dowels are generated, and these generated with reference generated, the casting is given to the machine shop or the customer. So there is less of friction between 2 parties at a later date. So that is what is casting averaging. So typical casting averaging fixture is seen here. There are bumping rods so that casting is lowered on a spring-loaded locator. Then it rests on the fixed locator. Then there are screw jacks so that it can be moved. There are templates coming from sides. So these templates will ensure that all proper profiles of the castings are matching with the reference. And then you generate 2 or 3 spot facings and 2 dowels. It goes for machining. This is something which is say 50-year-old or 60-year-old machining practice being followed even today in many of the companies. But with advanced manufacturing, casting manufacturing processes and machining processes, many of the customers, particularly Europeans, have shifted to 3-to-1 location. We have made the casting and we have ensured that the casting is proper with reference to the defined reference parameters, and the customer machines the same casting with predefined machining references. So with this averaging operation has now been eliminated, maybe in 30 to 40% of the cases. Now, what are the modern trends in foundry and tool making? With robots coming and more automated machines coming and the huge machines coming like 8 tons, as I said, all cores needed per mold in one shoot of the core box or a cluster of core boxes. So you change the entire cluster of core boxes and the whole setup changes. So there is nothing like making core storage and bring trolleys from different locations, assemble them. It goes as a continuous process. Then candleless core making is again a new concept. Of course, now it is stabilized. Horizontally versus vertically parted core shooters, we discussed about this. Key core concept, robots in foundry, or which one has to visit foundries and see. Automated fettling and casting inspection and casting fettling fixtures. Modern tooling inspection techniques. Reverse engineering, solidification and flow analysis, core filling analysis. Now come to materials for foundry tooling. As I said, when we are making foundry tooling 40 years ago, wood and aluminum were the ones easier to hand machine. So that was used to make masters or the references, and then convert it into actual tooling or the cast iron tooling or SG tooling or steel castings. The next material is EN8 or OHNS, then P20 pre-hardened and H13. Each one has got a cost attached to it. H13 after machining will need heat treatment. P20 comes as pre-hardened around 30 to 32 HRC. Rest all are not hardened. So this is whatever the casting hardness that we get. Tolerances on tooling. What is desired? Meet all the machining constraints and parameters. Parting line gaps, finish, shape. CNC machining, people expect that since CNC is there, I'm going to get plus minus 5 microns, whatever, very easily. It is a misconception because if you machine a pattern, you need a tool which is almost 300 millimeters long. 300 millimeter long tool is going to have some tool deflection, some tool run out, some tool wear, tool form will have some variation. And because of this, the final machine part will differ from the desired part. So I'm not saying that because of this, all the inaccuracies are going to come, but one has to take care of these problems or counter these problems by his innovative means to finally achieve plus minus 100 microns of dimensional tolerance, three-dimensional tolerance on the tool. Now, tooling inspection reports. Earlier, we used to have height gauge and templates to ensure that the shapes are proper. Now, the same technology, the Mercedes cars were being made, where the tools were being made by this technology, and with today's technology also. Maybe people in those days were taking many times more efforts, but they were also delivering results comparable to what is being delivered today. So it's not that height gauge cannot give you correct dimensional answers. Then CMMs are, of course, today are very widely available, easily available. In fact, next stage has come, the scanners, different types, red light, white light, blue light. Now here, people feel that red light is inferior to white light and blue light is superior to white light. But these are all textbook observations. In reality, when we make a pattern, my tolerance or requirement of a pattern where sand grain is 200 microns, I'm very happy with 100 microns or 150 microns. It's not that I am happy. I have worked with General Motors USA also, and their tolerances are in that range, plus minus, plus 150 microns, minus 100 microns. So whether it is red light, whether it is white light, blue light, it gives you the same answer, same result. But people in their documents, they put blue light inspection is required, which is a misconception. Tooling cost optimization, we talked about so many things about tooling. Material selection has to be proper so that the tooling cost doesn't shoot up. Selection of foundry, appropriate technology, size of tooling, rigidity of the tooling, life of the tooling. If the life desired is 100,000, 200,000 castings, definitely tool has to be very rigid. The material has to be preferably P20 pre-hardened. Now we are coming to the end. Life and care for the tooling. Good design. Methoding has to be good, taking into account the points that we discussed. Core boxes, gating. customer changes and modifications, how easily we address these changes reflects on life and care for tooling. My advice would be never ever do changes by welding on the pattern or with MSeal on the pattern. Put a pocket, put an insert, remachine it. It's very easy with CNC machines, and you can achieve the same dimensional consistency and tolerance. Handling of the tooling has to be given a proper thought, because mishandling should not lead to, because the tooling is very heavy and mishandling can hamper the dimensional accuracies. Cleaning has to be very accessible and properly cleaned. If there is resin buildup on a tool of say 1,000 microns, 1 millimeter, there's no point in achieving 100 microns on the dimensional tolerances. Then storage. Foundry ends up with huge amount of tooling storage. So identification, retrieval, storage, keeping track of modifications is a huge task. But first one has to understand the task so that he can address it. Some tips: upkeep and reconditioning, no MSeal, no temporary corrections, put inserts, preferably screw from backside so that even screw heads are also not exposed to sand, no welding on tooling, monitor wear. If particularly this was true in case of epoxy toolings, where you can have a color strip embedded into the tooling, so that when that color strip wears off, maybe 200 microns, you come to know that this is the time for replacing the tool. Reference dowels. Reference dowels are very important. Should be part of tooling, should be part of drawing, should be part of culture, so that whenever you find something wrong on the casting or you get a feedback, you check the tool with respect to reference dowels. I have seen in General Motors foundry producing 3,000 tons a day. End of the day, every production, the core box goes to CMM shop, where there are battery of CMM machines, and the core box, the machine automatically goes, locates the reference dowels, checks the control points of the tool, and accepts or rejects the tool. Tool history card is updated. So whether that tool will go for production tomorrow or day after will depend on this periodic inspection. Reconditioning schedules also has to be there. Adequate manpower, always an issue. Glass bead or solid CO2 blasting, cleaning of fixtures, ease of movement, pattern ejection fixture. So with this, we come to the end.
Thank you, sir, for giving details
Bye.
of all the concepts related to foundry tooling, the details about patterns, parts of tooling, and the steps involved in tool design and manufacturing, and the maintenance and upkeep also.